Good day, everyone. Welcome to the second part of our discussion on mathematics in the modern world. My name is Mahid M. Manguntaram from the Mindanao State University main campus in Marawi City.
In the previous video, we got a chance to learn more about mathematics by answering the following questions. In particular, we have learned that mathematics can be seen everywhere since it is all about the unbelievable patterns of numbers formed by nature and by the universe. It also helps us understand nature and its various characteristics. This idea about mathematics is not entirely new. In fact, the great philosopher Galileo once said that the laws of nature are written in the language of mathematics. Our lesson will start by introducing the Fibonacci sequence and the golden ratio. Fibonacci, also known as Leonardo Pisano, is one of the best-known mathematicians of medieval Europe. In 1202, after a trip that took him to several Arab and Eastern countries, Fibonacci wrote a book titled Liber Abaci, which means Book of Calculation. In the said book, he introduced modus indorum, today known as the Indo-Arabic numeral system. He also explained why the said numeral system is more sophisticated and efficient compared to the Roman numerals. Fibonacci's book also contains a problem concerned with the birth rate of rabbits based on idealized assumptions. The solution of this problem which he obtained is a sequence of numbers that we now call the Fibonacci sequence. The Fibonacci's rabbit problem can be illustrated as follows. Number 1, at the start of a month, you have a pair of newborn rabbits. Second, after a month, the rabbits have just matured, so they are yet to produce any offspring. On the following month, the matured rabbits have produced another pair of rabbits. Every month thereafter, the matured rabbits produce another pair of rabbits while the offspring reproduce in exactly the same manner. From the illustration, we can see that the number of pairs of rabbits for the first 6 months are 1, 1, 2, 3, 5, and 8. In fact, we observe that the number of pair of rabbits for any month after the first 2 months can be obtained by adding the 2 preceding results. For brevity, we will refer to the terms of the Fibonacci sequence as Fibonacci numbers. Now, based on the previous illustration, we may establish a recursive definition for the Fibonacci numbers as follows. We let f sub n denote the nth Fibonacci number and let the first two terms be both equal to 1. Then, for n greater than or equal to 3, f sub n is equal to the sum of f sub n minus 1 and f sub n minus 2. Using this definition, we know that after the first 6 terms, we have 13, 21, 34, 55, 89, and 144, which will continue indefinitely. We define a golden rectangle as a rectangle whose side lengths are in the ratio 1:phi, where phi is approximately 1.618. Here, phi is popularly known as the golden ratio. The characteristics of a golden rectangle are attained by putting any two consecutive Fibonacci numbers as length and width. A golden rectangle can be broken down into squares the size of the next Fibonacci numbers down and below. If we break down a golden rectangle into smaller squares based on the Fibonacci sequence and divide each with an arc, we begin to see the Fibonacci spiral. It is also interesting to see that the quotient obtained when a Fibonacci number is divided by its preceding term is a number that is very close to the golden ratio. The significance of these numbers and patterns lie not from within but from where we find them. Let us consider this sunflower. Observe that the number of spirals displayed by its florets counts to 55 and 34, which are consecutive Fibonacci numbers. The same pattern behavior can also be seen in this pine cone. Other notable examples are the waves in the ocean, the weather systems, and especially the Nautilus shell. We can also see the Fibonacci numbers and spiral as well as the golden ratio in different parts of the human body. But the greatest occurrence of these numbers can be seen directly above us. At an average of 100,000 light-years across, even the galaxies follow the same pattern that was observed in our previous examples. In the earlier part of our discussion, we have learned that each term of the Fibonacci sequence are obtained by adding the last two terms. At this point, we will introduce another method for finding the Fibonacci numbers. For n greater than or equal to 1, we may solve for the nth Fibonacci number using the formula 1 over the square root of 5 times the quantity 1 plus the square root of 5 over 2 raised to the power of n minus the quantity 1 minus square root of 5 over 2 raised to the power of n. This formula is called Binet's formula, which was named after the French mathematician, physicist, and astronomer Jacques Binet. Now, suppose we want to find f sub 40. Using the recursive definition, f sub 40 is equal to f sub 39 plus f sub 38. However, the terms in the right-hand side are not given. This makes computation difficult since we need to repeatedly apply the definition before arriving at the desired result. On the other hand, Binet's formula can be used to solve for f sub 40 by simply letting n be equal to 40. As we can see, Binet's formula provides an explicit yet non-recursive way for finding the Fibonacci numbers. Another interesting point is the fact that this identity is approximately 1.618. Thus, even Binet's formula is actually expressed in terms of the golden ratio. This marks the end of our two-part lecture on mathematics in our world. Thank you for watching.